Imagine handing a general contractor just a quick napkin sketch of a house, right? And you just walk away. You say, hey, build it. You'll figure it out.
Right, which is a terrible idea.
Oh, completely. Because you'd come back, 3 weeks later and find the kitchen is in the basement.
Yeah.
The front door opens directly into a coat closet.
Yeah.
And, the plumbing is just completely incompatible with the actual city grid.
A total disaster.
Exactly. Yet this is exactly what millions of developers are doing, like right now with artificial intelligence. Welcome to a special deep dive into the source material, brought to you by the Data Zen AI Podcast, by the Data Zen community.
Glad to be here.
So usually, when you sit down to build software, there is this fundamental, just unquestioned assumption built right into your muscle memory. You open an editor, you type code, and that code is the absolute center of your universe.
It's the ultimate artifact, right? For the entirety of modern computing, everything surrounding the code, so like the architecture diagrams, the meetings, the product requirement documents, all of it has been treated as temporary scaffolding.
Yeah, just stuff to get you to the code.
Exactly. You put the scaffolding up to build the structure, but eventually, you tear it down because the machine only cares about the compiled code. The code is the actual building.
But the sources we're analyzing today are, they're asking a question that flips that entire reality completely upside down.
It really flips it on its head.
Yeah. What if code is no longer the main thing you produce? What if the specifications, like the actual written human-readable documents describing the intent of the software, what if they become the ultimate source of truth?
And the code just becomes an ephemeral byproduct.
Right. A byproduct that a machine just generates on the fly.
It sounds like science fiction to a lot of people. Or perhaps, a return to some of those failed architectural experiments of the early 2000s.
Oh, yeah.
But it is a massive paradigm shift. And it's gaining incredible traction right now, mostly because it's being forced upon us by the sheer volume and, honestly, the velocity of AI-generated code. We're moving toward this framework called Spec-Driven Development, or SDD.
So let's ground this in the reality of what most developers are doing today. Because if you look at the current landscape, we are living in the era of vibe coding.
Vibe coding, yeah, that's the perfect term for it.
It really is. Think about the last time you opened up an AI coding assistant, like Cursor, or GitHub Copilot, or maybe Claude Code. You probably just typed a really loose, highly contextual prompt. Something like, build me a user authentication screen with Google Oath and make it look modern.
Right. You hit enter, you watch the terminal light up, and you just sort of hope for the best.
And the seductive part of vibe coding is that, initially, you often get a surprisingly functional result.
You do.
The AI spits out a React component, it imports the right libraries, and the screen actually renders.
But the core issue here isn't that the AI lacks the ability to output syntactically correct code. It does that well. The issue is that we are treating these AI agents like search engines when we really should be treating them like highly literal, incredibly fast, but completely context-blind junior engineers.
Context-blind is the key there.
Exactly. AI models are astonishingly good at statistical pattern completion. But, they cannot read your mind.
Right, because when you give an LLM a vague prompt like make it look modern, you're essentially forcing it to make hundreds of invisible micro-decisions on your behalf.
Which is terrifying if you think about it.
Oh, absolutely. It has to guess your routing strategy. It has to assume your security constraints. It might even hallucinate a dependency on some library that your enterprise doesn't actually approve of.
Yeah, and because you didn't explicitly tell it how to handle, say, state management, it just invents a pattern.
Yeah.
And that pattern quietly breaks a data flow 3 directories away.
So you get speed, sure, but you are building a complete house of cards.
Which brings us to the core mission of this deep dive. Spec-Driven Development is basically an attempt to enforce structural integrity onto this totally chaotic new workflow.
Right. And to really understand how it works, you have to contrast it with the traditional software development lifecycle, the SDLC.
Yeah, the old way. The traditional SDLC moves in a very linear, very predictable sequence. You gather requirements, you move to development, you write the code, and then you enter this perpetual cycle of fixes and maintenance.
Never-ending cycle, really.
Oh, yeah. And in that model, you might write a product requirements document, a PRD, but the moment the developer starts typing actual variables and functions, that PRD is effectively dead.
Yeah, it gets shoved into a shared Google Drive somewhere and is never looked at again. Unless, a compliance audit happens.
Exactly. But spec-driven development reroutes that entire flow. The new pipeline is define intent, generate, and then refine.
Define intent, generate, refine.
Yes. The central thesis here is that the code serves the specification, not the other way around. You aren't just writing a passive text file for humans to read anymore. You're writing an executable artifact.
Okay, an executable artifact? What does that mean practically?
It means the AI agent actually reads your structured intent and mechanically executes it to generate the implementation.
And I can already hear the collective groan from veteran engineers listening to this.
Oh, I'm sure.
Because anyone who has been in the industry for like more than 5 minutes will tell you that getting teams to write good, comprehensive specifications is a battle we have been losing for decades.
It's the oldest fight in engineering management.
Right. So the natural pushback from you listening might be, well, if specs are so great, why haven't we always built software this way?
It's a fair question. And the insights from XCapit, they're a firm that focuses heavily on AI-augmented development workflows. They actually break down the historical failure of manual specification into 4 specific systemic modes.
Let's walk through those. The first failure mode is ambiguity, right?
Yeah, ambiguity. Because natural language is just an inherently messy, low-bandwidth way to transfer technical information. It's incredibly imprecise.
Give me an example of that.
Sure. Consider a really simple, standard requirement you might see in a JIRA ticket today. Something like, the system should handle high traffic gracefully.
Oh, gracefully. I love that word.
Right. To a product manager, gracefully just means the user interface doesn't show a 500 internal server error.
Just don't let it crash on the stream.
Yeah, exactly. But to a back-end database engineer, gracefully means implementing query caching and connection pooling. And to a site reliability engineer, it means spinning up auto-scaling container clusters and configuring load balancers.
Wow.
So because the specification is ambiguous, every single one of those interpretations becomes an implicit decision that an individual developer just makes in a silo, usually without aligning with the rest of the team at all.
Yeah. The word gracefully is practically poetry. It has literally no place in a system architecture.
None.
So we fail at ambiguity. But, even when we really try to be precise, we hit the second failure mode, which is incompleteness.
Yes.
It seems like human beings are just biologically wired to only describe the happy path.
Oh, always the happy path. We document exactly what happens when the user types in their password correctly, they click the login button, and the server responds perfectly.
Because enumerating edge cases is just cognitively exhausting.
It's brutal. Think about what actually happens in a real-world system. What happens if the database connection drops exactly halfway through the token generation?
Right.
Or what happens to the in-flight network requests if the user session expires while they are literally in the middle of uploading a file?
Or what if the file they're uploading is actually a disguised executable instead of a JPEG?
Exactly. Documenting every single one of these failure modes takes hours of tedious, completely unrewarding mental labor. Humans naturally skip this step to get to the quote-unquote real work of coding.
And those undocumented edge cases, that's exactly where the catastrophic production bugs live.
That's where they hide.
It's basically the technical equivalent of sweeping dust under the rug.
Yeah.
It's there, but dealing with it is just too tiring.
Yeah.
But let's say you have a superhuman engineering team. They eliminate ambiguity. They document every single edge case. They still run into the third failure mode, staleness.
Staleness is inevitable. The half-life of a software specification's accuracy is measured in days, sometimes even hours. Code simply moves faster than documentation.
Yeah, I've seen that a million times.
Right. 2 weeks into a sprint, a developer hits an unexpected roadblock with a third-party API. They suddenly realize the original architecture and the specification just won't work, so they pivot.
They rewrite the function, they change the data schema, they push the code.
And they almost never go back and update the original specification document. Because in engineering culture, updating documentation is often viewed as low-status work. It doesn't ship features, and it doesn't resolve active tickets on the board. So within a single fiscal quarter, your pristine specification is nothing but a historical artifact. You just learn to completely distrust it.
And once you distrust the spec, you have to go read the raw code anyway, just to understand what the system actually does.
Exactly.
Which leads perfectly into the fourth and final historical failure mode, cost. Writing truly rigorous, unambiguous, complete specifications manually is just an incredibly expensive use of human capital.
The economics of manual specs have basically never made sense for agile teams. I mean, if you ask a senior backend engineer to write a detailed API specification for a moderately complex microservice,
We're talking defining every data schema, every error catalog, every routing constraint.
right, that might take them 3 weeks. You are paying a premium salary for someone to write documentation rather than shipping the actual product.
And when you multiply that labor cost across an entire enterprise organization, the math just completely falls apart.
It does. Most development teams rationally calculate that the cost of writing perfect specs far exceeds the cost of just fixing the bugs those specs would have prevented.
This is where we arrive at the great irony of the current moment. Artificial intelligence, specifically large language models, they cause this current crisis of vibe coding, right? Because they made generating code so frictionless that we just abandoned planning altogether.
Yes.
But those exact same LLMs are the catalyst that completely solves the 4 historical failures of specifications we just walked through.
It's a fascinating paradox.
How does an LLM mechanically fix the economics of spec writing?
Well, AI radically alters the cost-benefit analysis of rigor. It doesn't replace the human's architectural judgment. Instead, it completely absorbs the mechanical, exhaustive, tedious translation work that humans absolutely despise.
Okay, think about how an AI agent handles that incompleteness problem we talked about.
Right. So a product manager can write a natural language intent. Something like, we need an endpoint for profile photo uploads, maximum 5 megabytes, strictly JPEG or PNG formats.
And a human would usually just stop there.
Exactly. But an AI agent, properly prompted within an SDD framework, instantly transforms that single sentence into a comprehensive, structured, open API specification.
It's basically acting as a translation layer between human intent and machine constraint.
Yes.
When you say it transforms it into an open API spec, what is the AI actually doing under the hood there?
It is mechanically deriving all the unstated technical implications. So it takes the profile photo intent and automatically structures the multi-part form data HTTP request schema.
Oh, wow.
Yeah. And it explicitly defines the 413 payload too large error code for when the file exceeds 5 megabytes. It defines the 415 unsupported media type error for when someone, tries to upload a PDF instead of a JPEG.
It generates the boundary constraints.
The LLM essentially acts as an exhaustive checklist engine. It doesn't get tired. It doesn't experience cognitive fatigue when mapping out 20 different failure states for a single file upload.
So it makes rigorous specification cheap. And it eliminates the ambiguity because the AI forces that natural language into a compiled standard format like OpenAPI.
Exactly.
But this brings up a massive spectrum of execution because writing a spec is a really fluid concept.
Highly fluid.
I mean, it can mean jotting down 3 bullet points in a text file, or it can mean generating a 50-page architectural thesis. If you are a developer listening to this, how much structure is actually required to make spec-driven development work without grinding your momentum to a complete halt?
That tension between rigor and speed is exactly what researcher Deepak Babu-Piskala addresses. He has this analysis of the specification spectrum.
The specification spectrum.
Yeah. He breaks the modern SDD landscape down into 3 distinct levels of operational rigor. Because you don't have to radically overhaul your entire engineering department on day one. You can move along this spectrum based on the specific risk profile of the software you're actually building.
Okay. Let's dissect this spectrum. If I am building, say, a weekend prototype or just a quick internal tool, I assume I'm starting at level 1. What does level 1 look like?
Level 1 is known as spec-first development. In this workflow, you write a specification document before any code is generated, strictly to explicitly guide the AI's initial implementation.
So you're front-loading the context.
Right, to prevent the LLM from making those invisible micro-decisions we talked about. But here's the key distinction for level 1. Once the AI generates the code and the feature actually works, you are allowed to abandon the spec.
Oh, really?
Yeah. The specification acts as a highly structured launchpad, but it does not have to be maintained indefinitely.
So it's essentially just a highly disciplined multi-paragraph prompt. You use it to get the AI pointed in the exact right direction, but you aren't committing to updating that text file every time you refactor a variable 6 months later.
Exactly. It prevents the initial hallucination phase of vibe coding,
Yeah.
but the long-term maintenance cost of the spec just isn't justified for a disposable prototype.
Makes sense.
However, if you are building professional, long lifecycle software, you move to level 2. This is called spec-anchored development, and it is widely considered the pragmatic sweet spot for modern engineering teams.
Spec-anchored. Meaning the code is physically tethered to the specification document.
Yes.
How does that practically work in a code base, like day to day?
In the spec-anchored model, the specification is living documentation. It resides directly in the repository alongside the source code. They are treated as twin artifacts.
Okay.
If the business logic dictates that a behavior must change, you are required to update both the spec and the code. But as we know, human discipline fails.
Right. People get lazy.
Exactly. So the critical mechanism here is automated enforcement. You use CI/CD continuous integration and continuous deployment pipelines that actually fail your build if the code drifts away from the specification.
Stop there, because that is the magic trick right there.
It really is.
How does a CI/CD pipeline, which usually just runs unit tests and checks for syntax errors, know that a Python script has drifted from a markdown text file? Like, what is the actual mechanism?
The mechanism relies on contract testing and executable schemas. Let's say your specification is written in an API blueprint format or OpenAPI.
Okay.
When a developer pushes a new commit to the repository, the CI/CD pipeline spins up a localized, automated testing environment. It reads the specification file and mechanically generates a mock server or a test suite based purely on that document.
Wow. Based purely on the spec.
Yes, and then it fires automated requests at the newly written code. So if the developer tried to sneak in a quick fix, let's say they changed an API response field from user to accounted in the code, but they forgot to update the spec, the mock server immediately catches the mismatch.
Oh, that's incredible.
The pipeline throws a fatal error, rejects the code merge, and sends it back to the developer with a message saying, implementation violates specification contract.
That is brilliant. It completely removes the human element of forgetting to update the docs. The pipeline essentially acts as a ruthless bouncer at the door of your production environment.
A very ruthless bouncer.
If the code and the spec don't match perfectly, you just don't get in.
Yeah.
That forces discipline. So if level 2 is the sweet spot, what on earth is level 3?
Level 3 is the extreme edge of the spectrum. It is called spec as source. And in this paradigm, the human developer is strictly forbidden from ever manually modifying the source code.
Wait, you never touch the code.
Never. You only interact with the specification document.
You just edit the markdown file and the entire application regenerates.
Yes. The code is entirely derived from the specification. If you find a bug in production, you don't open the Python or JavaScript file to patch it. You open the English specification, you clarify the logic that caused the bug, and you command the machine to regenerate the entire module.
That's wild.
There are actually frameworks entering private beta right now, like Tessel, that operate on this exact philosophical principle. They enforce this by injecting headers at the top of every compiled file that explicitly read. Generated from spec, do not edit.
Okay, I have to throw a massive red flag here.
I figured you might.
Because if you look at the history of software engineering, spec as source is not a new idea. It gives me intense déjà vu to the model-driven development, or MDD, crazes from like 15 or 20 years ago.
Oh, absolutely.
We used to draw these incredibly complex UML diagrams, hit a generate button, and pray that the tool spit out usable Java code.
And it rarely did.
It was universally hated because the generated code was unreadable, and the moment you needed to do something custom, the abstraction just completely broke down. So how is an AI reading an English spec any different from an old UML compiler?
Your skepticism is entirely justified, and actually the source literature explicitly draws this exact parallel to model-driven development. Yes, in certain highly regulated fields right now, like aerospace and automotive engineering, MDD is actually still the standard.
I didn't know that.
Yeah, engineers build visual logic models in a tool like Simulink. They run extensive simulations on the visual blocks, and then the tool generates certified, mathematically proven C code that goes into an airplane engine. No one hand edits that C code.
Okay, but building a web app isn't an airplane engine. The requirements shift daily.
Precisely. The critical difference today is the medium of the model. In the past, you were constrained by rigid proprietary visual diagrams. Today, the model is natural language processed through an LLM. English is the new modeling language.
Which is much more flexible.
Exactly. However, the exact same historical pitfalls remain, compounded by a totally new threat: LLM non-determinism.
Because LLMs don't produce the exact same output every time you ask them a question.
Exactly. LLMs are probabilistic text generators. You can feed an LLM the exact same specification document on Monday and Tuesday, and it might generate two slightly different architectural approaches to the code.
One might use a switch statement, the other might use a hash map.
Exactly. To rely entirely on Spec-Source, you need immense, unshakable trust in the generation tooling to be deterministic and stable. And for general-purpose software development, the AI models are simply not there yet.
So if Spec-Source is this experimental vision of the future, and Spec First is just a temporary crutch for weekend prototypes, then the actual battleground for professional engineering right now is that middle tier, spec-anchored development.
That's where the real work is happening.
But you can't just open a ChatGPT web window, paste in a prompt, and achieve spec-anchored development. You need dedicated infrastructure. You need orchestration.
You do.
And that brings us to the first major framework we are analyzing from the sources, GitHub Spec Kit. What exactly is this tool?
GitHub Spec Kit is a heavy-duty, open-source, CLI-based toolkit designed specifically to enforce spec-driven development. It is vital to understand that Spec Kit is not an AI model itself.
Okay, so it's not a new LLM.
Right. It is an orchestration layer. It interfaces with the AI agent you already use, whether that is Claude Code, GitHub Copilot, or Gemini.
Got it.
It sits on top of the AI and acts as a rigid project manager. It provides templates, guardrails, and sequential gates to stop the LLM from hallucinating or skipping steps.
So it's basically a framework to boss your AI around and force it to do the architectural paperwork before it is allowed to touch a single line of executable code.
That's a great way to put it.
Let's walk through the actual developer experience of using SpecKit. If I'm starting a new project, step one is establishing something called the constitution. What does that mean?
Before you attempt to build any feature, you run a command in your terminal, /specit.constitution. This triggers the AI to interview you and establish a foundational text file in your project directory.
Like a setup wizard.
Exactly. And this file becomes the immutable architectural DNA of your repository.
What kind of DNA are we talking about here?
It dictates the absolute, non-negotiable constraints that the AI must obey for the entire lifecycle of the codebase. So you define the tech stack. We are strictly using React Native with the Expo framework.
Okay.
You define the data layer. All database queries must route through the Supabase client. Do not write raw SQL. You define security protocols. Never, under any circumstances, commit secrets or API keys to the repository.
That seems so basic. Does telling an AI don't commit secrets actually change its behavior?
It does. Interestingly, the researchers at GitHub found that explicitly writing never commit secrets in the Constitution document was one of the single most effective constraints they tested.
Wait, really?
Yeah. LLMs suffer from context window degradation. When they are deep in the weeds of generating 1,000 lines of code, they just lose sight of the overarching security posture. The Spec Kit framework works by constantly taking this constitution file and injecting it into the system prompt of every single subsequent query.
It's a permanent anchor.
Exactly. Whenever the AI is forced to make a micro decision, it mathematically weights that decision against the rules in the Constitution.
So that solves the classic vibe coding problem, where the AI randomly decides to import MongoDB on day 3 of a project that exclusively uses PostgreSQL. The Constitution forbids it.
Exactly. It can't break the rules.
Okay, the DNA is set. Now I want to build an actual feature. Let's say I need a complex user onboarding flow. SpecKit forces you through a 4-phase gated workflow. Unpack phase 1 for me.
Phase 1 is initiated with the /specit.specify command. In this phase, you are strictly forbidden from discussing code.
No code at all.
None. You provide the AI with a high-level intent, and it generates a detailed specification document focusing entirely on the what and the why. You're mapping out user journeys, defining the business value, and outlining the expected outcomes.
Like, who is the target user? What specific problem does this onboarding flow solve? What data must be collected?
Precisely. And the crucial mechanism of SpecKit is that it is a gated workflow. You stop here, the terminal halts.
It waits for you.
Right. The AI generates a spec.md file, and as the human orchestrator, you must read it. You look for logic gaps, you correct any hallucinations regarding the user journey, you explicitly sign off on this document. The system will not allow you to advance to phase 2 until phase 1 is perfectly aligned with human intent.
Okay, so I read the spec.md file. It perfectly describes the onboarding flow I want. I approve it. How does SpecKit transition from that abstract business logic into actual technical architecture? What is phase 2?
Phase 2 is the /specit.plan command. This is where the translation happens. The AI agent reads the approved spec.md from phase 1, it cross-references it with your immutable rules in the Constitution, and it generates a comprehensive technical plan.
But how does text prediction actually generate a reliable technical plan? Like, how does it evaluate trade-offs without actually thinking?
It doesn't think, but it processes structured comparisons really well. The Spec-Kit framework prompts the LLM to analyze the specification and generate potential architectural approaches.
No, I see.
So if the spec requires real-time data updates, the LLM will map out the trade-offs between using WebSockets versus server-sent events. It weights those options against your constitution. It defines the exact data schemas needed. It drafts the API contracts.
It identifies which legacy systems will need to be integrated and flags potential friction points.
Right. It produces a plan.md file that serves as an engineering blueprint.
And again, we hit a gate. We stop and read the plan. I check to make sure the AI didn't decide to invent a completely new state management library or use an archaic routing method. I verify the trade-offs. Once I approve the plan, we move to phase 3.
Phase 3 is executed via /specit.tasks. The agent takes a verified specification and the verified architectural plan, and it begins to fragment the work.
Fragmenting.
Yeah, it breaks the entire feature down into isolated, actionable, granular tasks and outputs a tasks.md file. But this is not merely a bulleted list. It organizes these tasks using a directed acyclic graph, a dependency map.
Explain how that dependency mapping works. How does it know what order to build things in?
The LLM analyzes the data flow of the architecture. It mathematically deduces that it cannot build the React front-end component until the API endpoint exists to feed it data. And it cannot build the API endpoint until the database migration is written to store that data.
So it sequences the tasks chronologically.
Furthermore, it analyzes which tasks have no overlapping dependencies and marks them with a special P tag, indicating they can be executed in parallel by multiple subagents.
That is project management on a level that most human engineering managers struggle to maintain.
It really is. And it goes one step further. Spec-Kit structures the task list using strict test-driven development, or TDD, principles.
TDD, okay.
Before it lists a task to write the database migration, it explicitly creates a preceding task that says, write the unit test verifying the database migration fails if the table doesn't exist. It plans the tests before the implementation.
So by the time I approve this task list, I have a specification, an architecture plan, and a perfectly sequenced test-driven roadmap. And I haven't written a single line of code. But the entire intellectual heavy lifting is completely done.
That's the magic of it.
Which brings us to the final gate, phase 4.
Phase 4 is /specit.implement. The human steps back, and the agent takes over the terminal.
Finally.
Right. It reads the tasks.md file and executes the sequence one by one. For task 1, it validates the prerequisites, it writes the unit test, it runs the test, and confirms that it fails, proving the test is valid.
Right. Checking for false positives.
Then it writes the implementation code, it runs the test again and confirms it passes. Then it checks off task 1 and moves to task 2.
So as a developer, my day-to-day reality completely shifts here. I'm no longer staring at a blank IDE typing syntax. And I'm no longer reviewing massive 1,000-line pull requests generated by a chaotic vibe coding session.
No, not at all.
I am reviewing hyper-focused, isolated file changes that are directly tied back to a mathematical dependency graph, which is tied to a technical plan, which is tied to a business specification.
Exactly. You are transitioning from being a manual code typist to becoming a systems architect. You are the product manager for an autonomous coding agent. The machine provides the mechanical execution and the exhaustive syntax generation. You provide the architectural judgment and the business context.
And what makes this framework so fascinating is the ecosystem that the open source community is building around it right now. The source material highlights that there are over 30 extensions already built for Spec-Kit.
The ecosystem is growing fast.
You have plugins like Spec-Kit Azure DevOps, which automatically takes that generated task.md file and syncs it into Azure Work items for your enterprise tracking. You have Spec-Kit DocGuard, which constantly traces your implementation back to your documentation to ensure nothing rots.
But the extension that really stands out,
The Red Team one. Spec-Kit Red Team. It blew my mind.
the adversarial multi-agent extension, it is a brilliant concept.
It really is.
Yeah.
Explain how this works to everyone, because injecting adversarial agents into a local development workflow feels incredibly futuristic.
When you run the /specit.red team command, typically right after generating your initial specification in phase 1, the framework spins up several parallel AI agents. But these agents are not designed to help you build the software.
What do they do?
They are explicitly prompted with an adversarial persona. Their sole purpose is to attack your specification document.
They act as automated critics.
Exactly. One agent might be prompted as a malicious security hacker. It scans your spec looking for prompt injection vulnerabilities, missing authentication middleware, or unprotected data endpoints.
Wow.
Another agent might be prompted as a pessimistic site reliability engineer. It looks for logical loops that could cause a denial of service or missing timeout constraints on third-party API calls.
So they just bombard your spec with simulated edge cases?
They essentially argue with your proposed logic. They force you to patch the holes in your logic before you advance to the planning phase, ensuring the specification is bulletproof before a single line of code is ever generated.
Using SpecKit sounds incredibly rigorous, and the resulting architecture must be incredibly robust. But we need to do a reality check here.
Always.
Using SpecKit for a quick button color fix or a minor styling update is like filing a massive environmental impact report just to plant a single tomato seed in your backyard.
That is the perfect analogy. The sheer weight of SpecKit is its biggest drawback. It generates a mountain of markdown files, a constitution, a spec, a plan, a task list, a test suite.
It's a lot to manage.
If you are building a massive enterprise microservice from scratch, that audit trail is invaluable. It provides compliance, it provides clarity, and it allows massive terms to align. But if you are a solo developer trying to quickly iterate on an existing code base, the four-phase gated workflow is just paralyzing overhead.
Which is exactly why the engineering community hasn't just standardized on SpecKit alone. The sources provide a deep analysis of a completely different methodology detailed by software architect Ali Raza. It is called OpenSpec.
OpenSpec, yeah.
If SpecKit is the heavy enterprise sledgehammer, what is OpenSpec?
OpenSpec is a lightweight, highly flexible alternative designed to bridge the gap between the chaos of vibe coding and the extreme rigor of SpecKit. It strips away the heavy gating and focuses on continuous, localized alignment.
Okay, localized alignment.
And crucially, while SpecKit shines in greenfield projects, meaning brand new, 0-to-1 code bases, OpenSpec is specifically optimized for brownfield development.
Brownfield meaning you are parachuting into a massive, existing, messy legacy code base that has been around for years.
Correct. In a brownfield system, you cannot realistically generate a comprehensive master specification for the entire application up front. It would take months. OpenSpec relies on a much tighter core loop. Propose, plan, implement, archive.
Let's break down that loop. Raza used the example of building a React Native mobile app. How does OpenSpec handle that process differently than SpecKit?
It starts similarly. You still establish a lightweight constitution file to ground the AI specifying tools like the Expo framework, Tailwind CSS for styling, and a Supabase backend. But the daily workflow is vastly more iterative.
Right.
Instead of forcing the AI to generate a master task list for the entire application, you focus on one microfeature at a time.
So, propose. I tell the AI I want to add a forgot password screen.
Yes. You propose the change. The AI instantly reads the constitution and your existing code base, and it outputs a highly localized plan for just that feature. You approve it, and it implements the scaffolding.
Simple enough.
But the defining mechanism of OpenSpec is the final step. Archive.
What exactly does the archive step do? Because if I'm building feature by feature, won't I just end up with 50 scattered markdown files?
The archive command prevents that exact fragmentation. Once the AI successfully implements the forgot password feature and the code compiles and tests pass, you run the archive command.
Okay, and then what?
The AI takes the localized plan it just executed and autonomously merges the relevant architectural details into the project's single main spec document. It cleans up the temporary files, updates the central source of truth, and clears the stage for the next feature proposal.
That is a fundamental difference in philosophy. It seems almost like you are building the specification backward as you go. You are organically growing the central documentation feature by feature, rather than attempting to write a monolithic Bible up front.
That is an excellent way to conceptualize it. To summarize the operational differences for anyone deciding which tool to adopt, SpecKit is highly structured, gated, and procedural. It creates an exhaustive paper trail.
Great for enterprise environments,
Yeah.
high compliance industries, or 0-to-1 builds where architectural failure is catastrophic.
Right. And OpenSpec is fluid, iterative, and localized. It simply forces you to explicitly agree with the AI on what to build just before the code is written, ensuring continuous alignment without bogging you down in project management overhead.
Okay, so we have covered the theory. We have dissected the mechanics of both SpecKit and OpenSpec. But theory only matters if it survives contact with reality.
Very true.
Let's look at the concrete business cases. Where does spec-driven development actually move the needle, and where does it just fall flat on its face? Let's start with the massive wins. Where is SDD undeniably the right choice?
According to the implementation data from XCapit, the strong fit scenarios are universally found in environments where contract stability is the paramount concern. We are looking at heavily API-driven systems, sprawling microservice architectures, regulated industries like digital healthcare or finance.
Right, anywhere failure is expensive.
Exactly. And scenarios involving large teams where product managers and developers historically suffer from severe communication breakdowns.
Let's drill into the specific financial services case study mentioned in the sources, because the numbers attached to this are staggering. Walk us through exactly what this company was facing and how SDD fixed it.
So this financial firm was suffering from chronic integration failures. They had multiple isolated teams building different microservices. Team A would build a front-end dashboard, and Team B would build the back-end API to feed it data.
A classic setup.
But because they were relying on ambiguous JIRA tickets and verbal agreements, the data structures never matched. When they tried to connect the systems in the staging environment, the APIs would constantly break.
Because Team B assumed the amount field was an integer, and Team A built the front end expecting a string with a currency symbol. The classic mismatch.
Precisely. The integration phase became a total nightmare of debugging and finger-pointing. To solve this, leadership mandated a strict API-first, spec-driven approach using OpenAPI standards and a contract testing tool called Specmatic. They entirely inverted the workflow. Before a back-end developer was allowed to write a single line of business logic, they had to write the OpenAPI specification.
And how did the front-end team keep working if the back-end didn't even exist yet?
This is where the executable nature of modern specs comes into play. They took that OpenAPI document and ran it through a generator to instantly spin up a mock server.
A mock server.
Yeah, the mock server didn't have a real database behind it, but it perfectly mimicked the exact inputs and outputs defined in the spec. The front-end team connected their dashboard to this mock server and began building their UI immediately with 100% confidence that the contract was stable.
So they paralyzed the development. But what happens when the back-end developer finally writes the real code and they make a mistake that violates that original spec?
They utilized that CI/CD pipeline mechanism we discussed earlier. They placed validation checks directly into the continuous integration flow. If the backend developer pushed code that drifted even slightly from the OpenAPI spec, the pipeline immediately threw a fatal error and blocked the merge.
The bouncer at the door.
Exactly. The code could not reach the integration environment unless it mathematically proved it adhered to the contract.
And what was the measurable business outcome of this process shift?
They achieved a 75% reduction in integration cycle time.
A 75% reduction. That isn't just an incremental agile improvement. That is a complete structural transformation of how fast a company can deliver software.
It's massive.
And it is entirely because they stopped arguing about code in the staging environment and started agreeing on contracts before the code was written.
Exactly. When an incompatibility is caught at the specification review stage, when it is just a markdown file, it takes 5 minutes to resolve.
Right.
When that same incompatibility makes it into the production code base, it takes days of cross-team coordination, debugging, hotfixes, and deployment pipelines to resolve. XCapit essentially drank their own champagne on this concept.
What do you mean?
They used an SDD approach to build their Argentor multi-agent framework. They leaned on 483 automated tests derived directly from formal specifications. It is a proven methodology at scale.
But to bring balance to the discussion, we have to look at the other side of the coin. If I am an engineering lead listening to this, getting fired up about CI/CD pipelines and OpenAPI specs, what is the specific scenario where I should tell my team to put the specification tools away and just vibe code?
You should explicitly avoid SDD whenever the operational overhead of writing the specification exceeds the value of the stability it provides.
Give me an example.
The most obvious example is early-stage throwaway prototyping. If you are building a proof of concept for a startup pitch, your only goal is to discover what you should be building. You are seeking market validation.
You don't even know what the edge cases are yet, let alone how to document them.
Exactly. If you are doing highly exploratory R&D, perhaps experimenting with a new machine learning model or a novel physics engine, you cannot specify the behavior in advance because you are discovering the behavior through the act of writing the code.
That makes total sense.
A rigid specification framework will actively suffocate that discovery process. The same logic applies to one-off utility scripts. If you need a quick Python script to parse a CSV file and upload it to a database one time, do not waste time generating a constitution, a plan, and a test suite. Write the script, run it, and delete it. SDD is for systems that need to endure.
So the rule of thumb is, if the code's lifespan is measured in hours or days, skip the spec. But if the software needs to survive for years and be maintained by people who didn't write it, this shift toward SDD feels absolutely inevitable.
It does.
And there is rigorous academic science backing up exactly why this shift is necessary in the era of generative AI. Let's dive into the research. The sources reference a highly influential Archimedes paper titled Rethinking Software Engineering for Agentic AI Systems. What is the profound paradigm shift they are analyzing there?
The authors of the paper make a brilliant macroeconomic observation about the nature of our industry. For the last 50 years, the entire discipline of software engineering has been built on a single fundamental assumption. Writing code is the central rate-limiting activity of the development process.
It's what takes the most time.
Right. Productivity has historically been measured by how many lines of code a human being can manually type and compile in a given week. Code was a scarce resource.
But LLMs have completely inverted that reality. We now live in a world of infinite code.
Exactly. With the advent of AI coding agents, code is no longer a scarce resource. It is an abundant, disposable, instantly generated commodity. You can ask an AI to generate a 1,000-line routing module in 3 seconds.
Wow.
But because code is now infinitely abundant, the bottleneck in software engineering has shifted downstream. The new crisis is verification.
Verification. How do we prove that this infinite, rapidly expanding mountain of AI-generated code actually does what we need it to do, securely and reliably, without quietly introducing catastrophic vulnerabilities?
Precisely. And this theoretical crisis is beautifully illustrated by empirical data. This leads us directly to the Borg et al. Study conducted at IBM using the watsonx platform.
Yes, the IBM study.
This is arguably the most crucial piece of empirical evidence in the entire source material.
Walk us through the methodology of this IBM study, because the findings are a massive reality check for the entire AI hype cycle.
Borg and his research team designed a rigorous 2-phase controlled experiment involving 151 professional developers. They wanted to measure the true lifecycle impact of AI-generated code.
Okay, so phase 1.
In phase 1, they asked the developers to write new features using AI assistance. They measured the time it took compared to a control group coding manually.
And the results of phase 1 were exactly what every AI marketing brochure claims, right?
Yes. The developers using AI experienced a 30.7% median reduction in task completion time.
That's a huge boost.
It was a massive productivity spike. AI undoubtedly makes humans type code faster. But the brilliance of the Borg study is that they didn't stop there. They initiated phase 2 to test the long-term reality of that code.
What did phase 2 look like?
In phase 2, the researchers brought in completely different developers. They assigned these new developers the task of maintaining, modifying, and evolving the code that was rapidly generated by the AI in phase 1.
And crucially, they had to do this maintenance without AI assistance, forcing them to manually read and comprehend the architecture.
Exactly.
So they were simulating the exact reality of enterprise software. The guy who wrote the code leaves the company, and 6 months later, you have to fix a bug in his module. What was the result?
The result was a complete collapse of the initial productivity gains.
Wow.
The researchers found absolutely zero significant improvement in completion time or code quality during the maintenance phase compared to the control group. Zero. In fact, they ran a complex Bayesian analysis calculating the probability distribution of maintenance times, which mathematically confirmed that any supposed maintainability benefits inherited from the AI-generated code were incredibly small and highly uncertain.
That is profound. The AI wrote the code 30% faster, but when the next engineer came along to read it and update it, they hit a brick wall. The 30% speed boost was essentially an illusion.
It was.
It was a localized sugar rush that completely evaporated the moment the code entered the maintenance phase.
It is the definition of generating technical debt at light speed. The critical takeaway from the IBM watsonx study is that raw speed gains from generative LLMs are real, but long-term software quality, security, and maintainability depend entirely on your underlying process infrastructure.
Not just the code generation.
Right. If you simply bolt an LLM onto a chaotic, vibe coding workflow without verification pipelines, architectural discipline, and formal specifications, you are not building faster software. You are just building an unmaintainable mess faster.
It's like building a skyscraper at 10x speed by wildly throwing steel beams together, but completely forgetting to pour the concrete foundation or draw blueprints.
Exactly.
It brings to mind the House of Cards metaphor referenced in the source material by engineering leader Adi Osmani. He quotes a personal rule from developer Simon Willison. What is Willison's rule?
Willison operates by a very strict personal philosophy. He says, I won't commit code I couldn't explain to someone else. It is a profound heuristic for the AI era.
Why is that rule so necessary right now?
Because AI-generated code is incredibly deceptive. When a junior developer writes bad code, it usually looks like bad code. It has weird formatting, confusing variable names, obvious syntax errors.
You can spot it a mile away.
Exactly. But when an LLM writes bad code, it looks highly professional on the surface. It uses sophisticated design patterns. It includes formatted block comments. It looks authoritative.
Right, it looks confident.
But beneath that polished surface, it can completely collapse under the slightest edge case that you didn't explicitly test for. It is a house of cards. Specifications act as the foundational bedrock that prevents that collapse. They force you to understand the intent before you accept the implementation.
But I need to push back again, because we have to stay grounded in the daily reality of developer. This all sounds intellectually pure, but practically speaking, I'm looking at the spec kit workflow. To build a feature, I have to generate a constitution file, a markdown specification, a markdown research document, a structured data model file, a markdown task list, and a markdown technical plan.
It's a lot.
Am I not just trading the fatigue of writing code for the extreme fatigue of reading endless markdown files? Honestly, reading thousands of words of AI-generated architecture plans sounds just as exhausting as debugging code.
Your concern is incredibly valid. And it is widely recognized by practitioners as a major tangible pitfall of spec-driven development. Tooling complexity and overwhelming file generation is a massive risk.
It feels overwhelming.
If you are not careful, you simply shift the cognitive load from the IDE terminal to the Markdown viewer. You can easily drown in generated intermediate documents.
So how do you mitigate that markdown fatigue? How do you stop the framework from strangling your productivity?
The experts recommend adhering strictly to the golden rule of specification. Use the absolute minimum level of specification rigor required to remove ambiguity for your specific context.
The absolute minimum.
Start simple. If you are building a small internal tool, do not adopt the entire 4-phase enterprise spec kit workflow. Use OpenSpec. Generate a single concise intent file, agree on it, and build. Do not let the framework dictate a level of bureaucracy that the project doesn't warrant.
Match the rigor to the risk. That makes sense. But there's another major pitfall mentioned in the sources, the risk of over-engineering the spec itself. What does that look like in practice?
Over-engineering the spec occurs when developers forget the purpose of abstraction. A specification is supposed to define the what and the why, but engineers are naturally inclined to solve the how.
Oh, I've done that.
So they start writing specifications that essentially read like pseudocode. They dictate the exact variable names the AI must use. They define the specific for loop structures. They mandate how a specific array should be sorted.
If you were doing that, you aren't writing a spec. You were just writing code with extra steps in English.
Exactly. When you tightly constrain the implementation details within the spec, you completely negate the primary benefit of using an AI agent. The AI is vastly better at rapidly generating syntax and optimizing standard loops than you are. By micromanaging the how, you bottleneck the machine.
So what's the alternative?
A robust spec defines the inputs, the outputs, the edge cases, and the constraints, and leaves the syntactical execution entirely to the agent.
The final pitfall we need to address is perhaps the most insidious: false confidence. Because I can easily envision a scenario where an engineering team adopts SDD, they write a detailed spec. The AI agent faithfully generates the code. The automated CI/CD pipeline runs the tests. Every single checkmark turns green, and the team high-fives each other and ships to production.
Right, the perfect deployment.
But they still end up shipping a catastrophically broken product to their users. How does that happen if all the tests pass?
It happens because a passing test suite in a spec-driven framework simply proves that the generated code perfectly matches the written specification.
Okay.
But what if the human being wrote a fundamentally flawed specification? What if the core business logic was wrong from the very beginning?
If you tell the machine to build the wrong thing, it will build the wrong thing flawlessly.
Precisely. And it will build it with terrifying speed. AI excels at mechanical completeness. It will ensure that every endpoint defined in your spec has a corresponding database table. But AI possesses absolutely zero real-world business context.
Zero.
If your specification dictates a pricing tier logic that accidentally gives premium access to free users under certain conditions, the AI will not question it. It will faithfully, perfectly, and rapidly implement the exact mechanism of your bankruptcy. This is why human judgment remains the irreplaceable core of software engineering. Never ship an AI-generated implementation without a human explicitly verifying the actual business logic of the specification.
The human is the ultimate arbiter of value. The machine is just the engine of execution.
Well, we have covered an immense amount of conceptual and technical ground today. Let's pull all of these threads together and definitively answer the massive questions we set out to explore at the beginning of this deep dive.
Sounds good.
I'm going to ask them directly. I want you to synthesize everything we have unpacked. Question 1. Do we genuinely need formal specifications again in the era of artificial intelligence?
Yes. We need them more desperately now than we ever did in the manual coding era. They're the only reliable, systematic way to constrain the inherent non-determinism of large language models.
Right. AI models are essentially highly educated probabilistic guessers. Specifications provide the mathematical boundaries that remove ambiguity. They form the necessary bridge between abstract human intent and precise machine execution. Without specs, you are simply vibe coding and praying that the AI guesses correctly.
Okay, question 2. Is spec-driven development ultimately going to replace the act of coding, or is it merely a framework for structuring it?
It is not replacing the creation of software, but it is radically and permanently shifting the role of the human developer. The era of the developer as a manual syntax typist is ending. You are transitioning into the role of a system architect and a strategic orchestrator.
As Ali Raza framed it.
Yes, you are becoming the product manager for your AI agent. The machine will handle the exhaustively tedious generation of syntax. Your core competency will be designing the system architecture, evaluating trade-offs, and verifying the logical outcomes.
And the final question, are tools like GitHub Spec Kit and OpenSpec actually solving real systemic problems? Or are we just layering a mountain of complex, bureaucratic markdown files over a process that used to be simple?
The honest answer is that we are doing both. We are unequivocally solving massively expensive problems. I mean, the 75% reduction in integration cycle times proves that SDD can eliminate the chronic integration failures, hallucinated code bases, and rapidly accumulating technical debt caused by unstructured AI use. But the operational complexity is very real. Implementing these frameworks requires a profound cultural shift within an engineering team. That is why you must aggressively defend that golden rule. Ruthlessly match the rigor of your specification to the risk profile of the project. Do not force enterprise-level architectural bureaucracy onto a weekend prototype.
It all comes down to intentionality. We are witnessing a fundamental pivot in the software industry. We are migrating from a historical world where the code is the ultimate source of truth to a future where human intent is the ultimate source of truth.
It's a huge shift.
And I believe that represents a massive, necessary upgrade for how we conceptualize and build complex systems. I want to sincerely thank you, the listener, for joining us on this incredibly detailed deep dive into the evolving, chaotic, and fascinating world of AI software engineering.
It is, without a doubt, one of the most exciting and disruptive periods to be working in this field.
To read the full article, analyze the exact CLI commands, and explore these concepts, tools, and workflows in even greater depth, head directly over to the datazen.top/podcast-A-25.
There is a wealth of practical material linked there to help you begin experimenting with frameworks like Spec-Kit and OpenSpec in your own repositories.
And please, when you visit the site, click the heart icon on the article. It is super important feedback for us. It is the primary signal that lets us know you find value in these rigorous technical breakdowns. And don't forget to subscribe to the Data Zen AI Podcast so you never miss out on future explorations.
Before we sign off, I want to leave you with one final philosophical thought to ponder. We have spent the last hour dissecting how artificial intelligence is becoming increasingly flawless at translating our natural language specifications into perfect, executable, compiled code.
Yes, the translation layer is getting incredibly thin.
If that technological trajectory continues, if AI agents reach a point where they are entirely reliable at deducing complex architecture from plain text, does English effectively become the ultimate final programming language? And if that is true, will the English majors, the technical writers, and the philosophers of today possess the core skills required to be the senior software engineers of tomorrow?
Wow. Now that is a paradigm shift to think about the next time you sit down, open your IDE, and stare at a blinking cursor in a blank prompt box. Thanks for listening, everyone. See you next time.